Welcome to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is microprocessor. Today, I will cover the rest of instruction set. In the earlier lecture, I discussed the arithmetic and data transfer instructions. Today, I will discuss another set of instructions. So, today I will start with the logical instructions. So, the logical operations, the commonly used logical operations are AND, OR, XOR, rotate, compare and complement. So, we will see these one by one. So, for AND operation, the instruction present in 8085 is ANA, that will AND the contents of A, that is the accumulator, with the operand mentioned in the instruction, that is R or M. So, it will logical AND the contents of these operands with the accumulator. So, in this case, sign 0 and parity flag are modified to reflect the result of operation. In all the arithmetic instructions, all the flags present in the flag register are modified. Similar is the case with logical. So, in every instruction I will mention what are the flags which are affected by the particular instruction. So, in this case, carry is reset and auxiliary carry is set in the ANDing operation. So, this ANA AB means that it will logical AND the contents of B plus A, and the result will go into A. Now, again ANI, it is the immediate addressing mode. It will logically AND the immediate data present in the instruction with the accumulator, and the result will go into accumulator. So, suppose the example is ANI 86H. So, it will logical AND the contents, that is the immediate contents present here with the accumulator, the contents of accumulator, and the result will go into accumulator. ORA, that is it will it will logically OR the contents of the present in the operand with the accumulator, and the flags which are modified are sign 0 and parity flags are modified to reflect the result, and carry and auxiliary carry are reset. So, and these are the examples. In this case, M denotes the contents of the register, contents of the memory location pointed to by the HL register pair, and here the B means the contents of B will logically OR with the contents of accumulator, and the result will go into accumulator. ORI, it is the immediate addressing mode. The contents mentioned here will be directly OR logically OR with the contents of accumulator, and result will go into accumulator. XOR, it means it will XOR the contents of these operands with the accumulator, and the result will go into accumulator. Here again the flags which are modified are these, and carry and auxiliary carry are reset. XRI, it is the immediate addressing mode with XOR operation. So, it will XOR the contents present in the operand with the contents of accumulator, and the result will go into accumulator. These are the flags which are modified according to this instruction, and carry and auxiliary carry are reset. So, this is the example. Here the 86 will be XORed with the contents of accumulator. When we talk about the rotate instructions, so there are certain categories, like either the carry will be rotated along with the rotation or it will not. So, according to this instruction, that is a RLC, that is rotate left with the carry, that is it will be rotated right, that is 7 will be rotated here, sorry, it will be rotated left, rotate left. So, in the rotate left instruction, so how will be rotated? 0, it will, this bit will be rotated here, this will be given here, this here, this here, and this here, and this bit will go into, means MSB will be rotated to LSB, and it will be shifted to carry also, but carry will not be rotated. Okay. So carry will not be rotated in this case. So here the carry is modified according to the bit 7. So as it is seen from the figure that the MSB will change the carry. So whatever will be the bit in the MSB, that will be copied to the carry, and so the carry will be changed. Sign 0 parity auxiliary carry, these are not affected. Example is RLC. RRC, that is rotate right with carry. So again here the contents are rotated to the right, means it can be seen here like, so this is the contents of accumulator. So this RRC, RLC, these all work with the accumulator. So here this is the carry. So this is right rotation. So in this way LSB will go to carry and LSB will also go to MSB in this way. So carry will not be rotated, but the contents of the accumulator are rotated with the carry. So again carry will be affected according to the LSB here. So contents, because contents of LSB are copied to carry also, and rest of the flags are not affected, and this is the example RRC. No need to mention any operand, because rotate instructions work with the accumulator only. Now again RAL, that is a rotate left along with the carry. RAL means with the carry, and RLC was with carry, and RAL is through carry. So what is the difference here? Let's see. So carry is also rotated in this case. So this is the left rotation. Yes, and the contents of MSB will be copied to carry, and the contents of carry will be copied to LSB. Again carry is modified according to bit, that is the MSB. Rest of the flags are not affected. Example is RAL. RAR, again the right rotation but through carry. So let's see with this example only, that this is the right rotation. Here the contents of these bits will be rotated, and along with this rotation the carry will be rotated. So in this way the carry will be modified and rest of the flags are not affected, and example is RAR. Compare instructions. So comparison means either the two operands will be, one will be greater or lesser or equal. So what is the instruction? That is a CMP. Here the operand can be R or M, and one of the operand is by default accumulator. So when we write CMP R or CMP M, so it means it will compare from the related to the accumulator. If the contents of accumulator are higher than this operand, then the no carry will be generated. But if the contents are lower than the operand, then carry will be generated, means the subtraction is from accumulator. So this is the comparison operation. So this is accumulator, this is another operand which is mentioned in the instruction. So if the contents of this operand is lesser than A, no carry is generated. If the contents of this operand is higher than A, then the carry will be generated, and if these two contents are equal, then 0 flag will be set. So this is the condition. So here few flags are affected, like carry 0, these flags are affected, and this is the example. This is the immediate addressing mode of compare instruction. Here the 8-bit immediate data will be compared with the accumulator. If this immediate data is less than accumulator, then no carry is generated. If this immediate data is greater than A, then carry will be generated. If both are equal, then 0 flag is set. So this is the condition. So example is CPI and any immediate data. Complement instructions means, complement means it will complement the value of accumulator, and the instruction is CMA. And here the no flags are affected. It is just changing the value of accumulator. It is just complementing it. CMC complement carry, that is the, if the carry is 1, it will be, result will be 0. If the carry is 0, it will be 1. So only the carry flag is affected, no other flags are affected. STC, that is a set carry. Carry is always set to 1 using this instruction, and no other flags are affected, only carry flag is affected. Again, the branching instructions. So branching instructions may be conditional or unconditional. So these instructions basically change the control flow to some other memory location, or we can say it will transfer the control flow, the program flow, to some other memory location. So the general syntax for this instruction is jump and some 16-bit address. So it can be conditional jump or it can be unconditional jump. This is unconditional jump. Simply writing jump 2034 will transfer the control flow to this memory location. So this is unconditional jump. Now let's see what are the conditional jumps. So we will have some condition here, and the operand will be 16-bit address. So suppose we are writing JZ 2034, it means jump if 0 is set. So if the 0 flag is, condition is always put on the flag register. Yes, so if any of the bits of the flag register is, so condition is always mentioned according to the bits present in the flag registers. So here jump if 0 flag set. So if the 0 flag is set at the time of execution of this instruction, then the control flow will move to 2034. Similarly, other are the conditions mentioned here. Jump if carry flag is set, jump if no carry flag, that is jump if carry flag is not set, jump if number is positive, that is the sign bit is 0, jump if number is negative, that is sign bit is 1, jump if 0, jump if the 0 flag is set, jump if not 0, jump if no 0 flag is not set, jump if parity is even, JPE. So if the parity flag is 1, then it will transfer the control flow to the memory location specified, and if JPO, that is a jump if parity is odd, that is if the parity bit is 0, then the program flow will be jumped, or we can say it will be transferred to the memory location mentioned in the instruction. So syntax is J, X and some location. So this is the syntax, and X denotes some condition according to the flags, and flags can be carry, parity, sign bit, 0 bit. Again, another branching instruction is call. So this is also the conditional call or the unconditional call. So general unconditional call is call 2034H. Here the program sequence will be transferred to the memory location mentioned here. And what is the difference between jump and call? That in the jump instruction, the program flow can get back to the main program when it encounters the return statement, return instruction in the subroutine. But when we are using the jump instruction, there is no chance, there is no provision of coming back to the main program. But in call instruction, there is the provision by writing the return instruction. Before the transfer, the address of the next instruction after the call is pushed onto the stack. So this is how it is happening, that before the transfer of the control, that is the transfer of the program flow, the address of the next instruction is pushed onto the stack, and after the execution, after the execution of return statement, the contents of the stack are again loaded into the program counter, and so we come back to the next memory location where we have left off. So this is how the sequence works. Now we talk about the conditional calls. This is same as the conditional jump instructions. Here the condition is denoted by X and 16-bit address again. So the same conditions, call if carry, call if not carry, call if positive, call if negative, call if 0 flag set, call if 0 flag not set, call if parity is even, call if parity is odd. Similar conditions are here also. Now that is the RST 0 to 7, that is a restart instruction, and it is, or we can say these are the software interrupts. The work of these instructions is also to change the program control according to the address mentioned in the vector table corresponding to these numbers. So, RST instruction jumps the control to one of the 8 memory locations depending upon this number, because RST 0, RST 1, RST 2, RST 3, RST 4 and so on up to RST 7. These all are having some vector addresses mentioned in the vector table, and according to the number mentioned here, the control flow will go to that memory location. So, these are basically the software interrupts. So, writing the RST3, it will transfer the program flow, or the program control flow will go to the memory location mentioned corresponding to this number. So, this is the restart address table. So, corresponding to RST0, the restart address is this, RST1 restart address is 8 and so on up to RST7. How we will find this restart address? So, you can multiply this number, that is, suppose I am taking RSTn, you will multiply n by 8, it will give you some decimal number, okay. So, you have to convert that decimal number into hexadecimal number, and this is this hexadecimal number, okay. So, what I am trying to say is that you can easily find the restart address of these RSTs numbers by multiplying this number, any of this number with 8, it will give you some decimal number, and you can convert that decimal number into hexadecimal number, it will give you the corresponding vector address. Then when we talk about the machine control instructions, NOP, that is a no operation instruction, is a very common one. This instruction is fetched and decoded, but no operation is performed. It is generally used to create some delay or to replace the instructions during the debugging. Another machine control instruction is halt. It will finishes the executing the current instruction and halts any further execution. So, an interrupt or reset is necessary to exit from the halt state. So, once the program comes into halt state, or interrupt or the reset is very necessary to come out of it. Now, DI, that is the disable interrupts, that interrupt enable flip flop is reset and all the interrupts except the trap, because trap is the highest priority interrupt and it is not maskable. So, it cannot be disabled using the DI instruction. So, this instruction is used to disable all rest of the instructions apart from trap. Again, EI, that is an enable interrupt, it is used to enable all the interrupts. RIM and SIM, these are two instructions, that is the first of all we will discuss SIM instruction. This instruction is used to implement 8085 interrupts, that is 7.5, 6.5, 5.5 and serial data output. So, what is happening here? Let's have a look at the syntax first. This is the first bit, that is SOD, the serial out data. So, whatever we want to send some data out of the microprocessor serially, then we have to write that bit here at SOD in the SOD line. So, this is the serial data enable. This is the master bit for the D7 bit. So, if this is 1, then this is enabled, otherwise not. This is undefined. This will reset RST 7.5. If this D4 is 1, then it is RST 7.5 will be reset, otherwise not. This is the master enable bit for mask set enable, that is the, if this bit is 1, so you can mask all these, otherwise you cannot. So, 1 here at any of these bits denotes it is masked, otherwise it is not masked. So, what is this syntax? This syntax is according to the accumulator. If whatever you want to write in these bits, bit number 0 to bit number 7, first of all you have to put that data into accumulator. So, then you will execute this SIM instruction. So, first of all, whatever you want to have according to this syntax, you have to write this full data into accumulator. Accumulator should be loaded with this data, and then you will execute SIM instruction, then it will work according to the functions mentioned here. So, this is how the SIM instruction is executed. And when we talk about the RIM instruction, it is the read interrupt mask. This sim was set interrupt mask and this is read interrupt mask. It will tell you the conditions of the masks interrupts according to this data. So here it is used to tell you the status of interrupts, all the interrupts, and read the serial data input. Whatever you want to write, whatever you want to read using the serial line, so you read from here. So how will you use this instruction? Suppose suppose you want to read the status of all the bits, then what will you do? You will execute this instruction and then you will read the contents of accumulator. So it will, after executing this instruction, the contents of accumulator are changed according to the functionalities mentioned here. What are the functionalities? This denotes serial input data bit. Whatever you have received serially, it will be reflected here at this bit. Then I7, I6 and I5, these are the interrupts pending bit. If the bit is 1, means if this bit is 1, it means interrupt 7 is pending. Then if this is 1, 6.5 is pending. If this is 1, then 5.5 is pending. And this is used to see if any of the interrupt is masked or not. If it is any of this is 1, it means that particular interrupt is masked, otherwise not. E is interrupt enable flip-flop. It is set if the bit 1 is if this is 1, it means the interrupt is enabled, otherwise not. So to read this condition, you have to read the contents of accumulator after the execution of rim instruction. So this is how rim and sim works and tells us the conditions or allows us to set the conditions for interrupts, but according to the accumulator. So these were all the machine control instructions. That's all for today. I have completed with all the instructions. In subsequent lectures, we will discuss further details about the microprocessors. Thank you.